Imagine a junior developer sitting at their desk for 4 straight hours, sweat on their brow, just trying to figure out why a React component isn't rendering or why a Python script is throwing a cryptic indentation error. In 2026, an AI agent takes that same error, scans the entire repository, and provides a fix in exactly 1.88 seconds. If your learning strategy is still focused on memorizing keywords, brackets, and basic boilerplate, you are essentially training for a job that no longer exists in the production environment. We are seeing a massive productivity gap where traditional syntax-first learners are being outperformed by those who understand how to drive the machine. The hard truth is that knowing how to write code is now a commodity, while knowing what to build and how it fails is the premium. The industry has moved on from the keyboard to the cockpit. In this lecture, I am going to tear down your old habits and show you what it actually takes to survive this era. But first, we need to understand how the definition of a developer has fundamentally changed and what that means for your career path. This is just the tip of the iceberg. Stay tuned to see how the very definition of a good developer has flipped overnight. In the old days, learning to code was a linear process. You learned the alphabet of the language, then the grammar, and eventually you wrote a sentence. This was the syntax-first era. But in the current landscape, this approach is a total failure. Production-grade engineering now follows a logic-first process. You start with the architectural blueprint, defining how data flows from a FastAPI backend to a PostgreSQL database and how it's cached in Redis. You define the logic, and the AI generates the implementation. If you can't visualize the architecture, you can't even write the prompt to get the code. I've seen many people struggle because they can't let go of the need to type every line manually, while others are building entire microservices in a weekend by mastering intent. The value has shifted from the how to the why. You need to understand the underlying principles of computer science, not just the flavor of the month framework. This architectural shift is the only way to stay relevant when the AI can write code better and faster than any human. Does this mean the language doesn't matter at all? I'll show you why that assumption is a dangerous trap in the next section. Welcome to the era of the language orchestrator. In the past, you were a Java developer or a Python developer, siloed into a specific ecosystem. Today, that boundary is dissolving. Language agnosticism is the ability to choose the right tool for the specific job, regardless of your personal familiarity with the syntax. If a high-performance service needs to be written in Rust, you use an AI to help you draft the memory-safe code, and then use your engineering principles to validate. The specific language matters less than the result. We are moving toward outcome-driven development where your value is measured by the systems you orchestrate, not the lines you produce. You might be managing a Go service, a Python data pipeline, and a TypeScript front-end simultaneously. Tooling has made the barrier to entry for a new language almost zero. This doesn't mean you're a jack of all trades. It means you are a master of the logic which applies across all stacks. The real value isn't in writing the lines. It's in knowing if those lines are actually right, and that requires a specific set of eyes. This way of thinking is what separates the high-level engineers from the prompt-dependent hobbyists. To wrap up this first chapter, we need to talk about the most critical skill for 2026, validation and review. When the AI writes the code, your role shifts from author to editor-in-chief. You must be able to spot a subtle logic flaw in AI-generated PR that might lead to a race condition or a security vulnerability. AI can be incredibly confident while being completely wrong, a phenomenon known as hallucination. If you don't have the deep technical foundation to review and debug that code, you're not an engineer, you're just a copy-paster. This is where your learning focus must shift. Instead of memorizing how to write a loop, you should be learning how to write tests, how to audit for security, and how to optimize for performance. You need to be the one who ensures that the code is not just functional, but scalable and maintainable. This chapter was about the why your old strategy is failing and why you need to pivot. Now that we've set the stage, let's look at the actual tools that still dominate the field. Speaking of survival, there's one language that refused to be replaced despite everyone saying it would: Python. Let's look at the Python paradox in the next chapter. In the field, we often hear that Python is slow and old, yet in 2026, it remains the undisputed king of AI. Why? It's not about the syntax, it's about the gravity of the ecosystem moat. When you look under the hood of PyTorch or NumPy, you aren't looking at Python. You are looking at decades of highly optimized C, C++, and Qt kernels. For a new language to kill Python, it doesn't just need a better loop, it needs to recreate 15 years of specialized mathematical libraries that the entire global AI infrastructure is built upon. In the real world, senior engineers don't choose Python because they love the global interpreter lock. They choose it because the cost of migrating away from these optimized C extensions is economically impossible. Python is the cockpit of a jet engine made of C++. While the cockpit is plastic, the engine is titanium, and you can't just swap the cockpit without grounding the entire fleet. This massive gravitational pull is what keeps AI development anchored firmly to Python. However, does this mean Python's performance issues are just ignored? Not exactly. The way we solve this reveals a massive gap between theory and practice. Let's talk about the performance gap that academics love to point out. Yes, Mojo and Rust are theoretically faster for raw execution. But in the 2026 AI-driven world, the metric that actually matters is development velocity. An AI agent can generate a functional Python script in seconds, and because Python is so permissive, that code usually runs. In contrast, when an AI tries to generate high-performance Rust, it often gets caught in borrow checker hell, requiring human intervention to fix memory safety issues. In a production environment, if your model needs to be updated every week, spending 3 weeks optimizing the execution time from hundreds to tens is often a net loss if it delays your release. We use Python because it allows us to fail fast and iterate faster than any other language. We trade execution CPU cycles for human and AI, engineering hours a trade that almost every senior lead will make in a heartbeat. But wait, if performance is so secondary, why are we seeing a rise in projects that try to bring Rust-like speed into the Python world directly? The reason Python persists isn't just the libraries. It's because Python is the ultimate glue language for the LLM era. In 2026, we aren't just writing code, we are orchestrating agents. These agents need to talk to a vector database, call a REST API, process a JSON payload, and then trigger a cloud function. Python's dynamic nature makes it incredibly flexible for this kind of pipelining. When an AI agent like GPT-5 or Claude 4 writes orchestration logic, it doesn't have to worry about complex type hierarchies or strict memory layouts. It just focuses on the flow of data. This forgiving nature of Python reduces the hallucination error rate in AI-generated code. In real-world projects, we see Python acting as the central nervous system that connects specialized components written in other languages. It is the common tongue of the AI age, much like English is for global business. It's not the most efficient way to communicate, but it's the one everyone knows. But this forgiving nature has a dark side, and that brings us to the rise of challengers who claim Python's lack of safety is a ticking time bomb. While Python reigns supreme in AI labs, the production environment of 2026 is a battlefield. We see TypeScript, Rust, and Go constantly challenging Python's dominance. TypeScript has won the edge in the web, Rust has won the infrastructure and the runtime, and Go has won the cloud-native microservices. In a real-world scenario, you might use Python to train your model, but you'll likely use Rust for the inference engine to keep latency low, and TypeScript for the user interface to ensure a snappy experience. The comparison isn't about which language is better anymore. It's about memory safety versus the ease of iteration. When AI generates code for these languages, the failure patterns are different. A bug in Python might take 30 minutes to find at runtime. A bug in Rust is caught in 3 seconds by the compiler. This trade-off is why we see a bifurcation in the industry, Python for the thinking phase and the others for the doing phase. Does this mean you need to learn all of them? Not exactly, but you need to know why AI prefers one over the other for specific tasks. Here is a counterintuitive truth. AI actually produces better code in strongly typed languages like TypeScript or Swift than it does in Python. Why? Because of the strict feedback loop. When an AI generates a TypeScript function, the type definitions act as a set of constraints that the AI must follow. If the AI hallucinates an object property that doesn't exist, the type checker flags it immediately. In Python, that hallucination might not be discovered until a user hits a specific button 3 days later in production. As a senior developer, I've seen that teams using AI to generate typed code have a 40% to lower bug rate in their initial drafts. The types provide the context that the LLM needs to understand the boundaries of the code. This is why, in 2026, we are seeing type-driven development become the standard for AI-assisted workflows. Python's lack of strict typing is its biggest liability in an automated world. If this is true, why hasn't everyone switched to TypeScript yet? The answer lies in how the domains are divided. In the end, 2026 isn't about one language winning everything. It's a domain sovereignty model. Python owns the intelligence, models, and agents. TypeScript owns the interface, browser, and mobile. Rust and Go own the foundation, infrastructure, and high-speed services. The mistake I see many juniors making is trying to learn the best language. There is no best language. There is only the best language for the specific layer of the stack you are building. If you want to work on AI agents, Python is non-negotiable. If you want to build the platforms those agents run on, you need to look at the challengers. The Python paradox is that it stays king not because it's the best at everything, but because it's the best at connecting everything. But even a king can fail if the code it produces is fundamentally broken, and that leads us to the most important part of this journey. We've talked about the strategy. Now let's look at the actual battle stories of when AI-generated code goes horribly wrong in production. Next up, battle stories, when AI code goes wrong. Your AI assistant just generated a 50-line Python script that handles concurrent API requests. It looks clean, uses the latest libraries, and passes the first 3 local tests. But once it hits production, the memory usage climbs steadily until the server restarts. This is the invisible bug, a result of AI producing syntactically correct but semantically flawed logic, such as failing to close a database connection pool or creating a circular reference in a complex closure. In the field, we see this constantly. Developers trust the perfect-looking output without understanding the underlying resource management. Python's garbage collector is powerful, but it's not magic. If the AI doesn't account for thread safety in a shared state, you're looking at a debugging nightmare that standard linters won't catch. This is the hidden tax of AI coding. The time you saved writing code, you often spend double in the middle of the night fixing it. But how exactly do we find the root cause when we didn't even write the code? Let's look at the professional survival workflow. When AI-generated code fails, your first instinct might be to paste the error back into the prompt and ask, why is this happening? Stop right there. In high-stakes environments, that's just gambling with your production stability. Professional approach is a disciplined 5-step root cause analysis. First, you must isolate the AI logic from the rest of the system to create a reproducible environment. Second, use tools like the Python debugger PDB or profiling libraries like Profile to step through the execution. Never assume a variable holds what the AI said it would. Third, verify the dependencies, as AI often hallucinates version-specific features that don't exist in your actual environment. Fourth, write a failing unit test that captures the bug. This is your ground truth. Finally, apply the fix manually based on your findings, not the AI's guesses. This process ensures you remain the master of the codebase, not just a spectator. If you skip these steps, you are simply building a house of cards. But wait, what happens when this house of cards grows into a massive enterprise system? That's where the real trouble starts. Speed is the ultimate trap in the AI era. Because generating code is now nearly free and instantaneous, developers are bloating codebases at a rate never seen before. We call this the spaghetti trap. You ask for a feature, the AI gives it. You ask for another, and the AI patches it on top. Without a senior's eye for architecture, you end up with a collection of loosely related scripts instead of a cohesive system. This creates massive technical debt. In production, we see Frankenstein services where different AI models wrote different parts of the same module, each using different naming conventions and logic patterns. The result is unmaintainable code that no human can understand 6 months later. To scale from a simple script to a robust system, you must prioritize modularity and clear interfaces over raw output speed. The question is, if the AI writes the code, what is your actual job? The answer lies in the high-level blueprints that the AI cannot design on its own. In 2026, knowing the syntax of a specific Python library is a low-value skill because AI has already indexed it all. The real value has shifted to high-level design patterns and solid principles. You need to be the architect, not just the bricklayer. While the AI can write a specific function, it doesn't understand why a strategy pattern is better than a giant nested if statement for your specific business logic. Professionals focus on dependency injection and factory patterns to ensure that when an AI-generated part needs replacing, the whole system doesn't collapse. Mastering these patterns allows you to direct the AI to build modular, testable components rather than just raw code blocks. This is the critical difference between a junior developer who copies prompts and a senior engineer who orchestrates complex systems. We've seen the dangers and the traps. Now it's time to map out the path forward. In the next chapter, we will reveal the exact 2026 roadmap you need to follow to stay ahead of the AI curve. In the past, we spent years mastering syntax and standard libraries, but by 2026, AI handles syntax better than most juniors. To survive, you must pivot to reverse learning. Instead of starting with Hello World, start with how the machine actually processes your code. If you're using Python, don't just learn lists. Understand how the CPython interpreter manages memory and why global interpreter lock GIL matters even in an AI-coded world. When AI generates a complex block of code, it often hides performance bottlenecks or memory leaks that a typical syntax-only learner will miss. I have seen countless projects fail because developers trusted in AI's logic without understanding the underlying garbage collection or compiler optimizations. You need to be the person who can explain why the AI's code is inefficient at the assembly or bytecode level. This deep dive approach turns you from a code consumer into a system evaluator. This shift is non-negotiable because if you can't debug the engine, you're just a passenger. But where exactly do we apply this deep knowledge? Let's look at the actual stack you need to master next. By 2026, the senior title isn't about how fast you type. It's about how well you orchestrate. Your focus must shift to system design and distributed systems. AI is fantastic at writing a single Python function, but it's remarkably poor at managing the data consistency between a microservice written in Go and a legacy database. You need to master the CAP theorem, distributed locking, and event-driven architectures. Think about high-load scenarios where thousands of concurrent requests hit your API. An AI might suggest a simple REST call, but a senior engineer knows when to implement a message queue like Kafka or a caching layer like Redis to prevent system collapse. In the field, the most expensive mistakes aren't syntax errors. They are architectural flaws that require months of refactoring. You must learn to draw the blueprint that the AI then populates with code. This means understanding how load balancers, container orchestrators, and database shards interact at scale. If you can't see the big picture of the data flow, the AI's code will eventually drown your system in technical debt. Does this mean you need to know every single language? No, you just need a strategic selection to build this moat. Here is the hard truth. Technical skill alone is a commodity in 2026. The ultimate career moat is deep domain knowledge. If you're building a fintech application, knowing the nuances of double-entry bookkeeping or real-time clearing systems is more valuable than being a Python expert. AI can write a sorting algorithm, but it doesn't understand the legal compliance requirements of a IPA in biotech or the millisecond latency requirements of high-frequency trading. Experienced engineers succeed because they translate complex business problems into technical constraints. When you sit in a meeting, you shouldn't just be thinking about how the AI will help with that. You must be thinking about what and why. Why are we choosing this specific database for these financial records? What happens to the data if the transaction fails halfway through? This domain-specific context is something AI lacks because it doesn't experience the real-world consequences of a system failure. By marrying your technical architectural skills with niche industry expertise, you become irreplaceable. But to execute these domain solutions, you need a specific toolkit of languages that work together. Let's define your strategic language portfolio for the next 3 years. To cover 99% of modern development in 2026, you don't need to be a polyglot of 20 languages. You need a strategic trio: Python, Rust, and TypeScript. Python remains the king because it is the lingua franca of AI and data science. You use it to glue services together and build prototypes fast. However, for the core engines where performance and safety are paramount, you need Rust. AI-generated code in C++ is often a security nightmare, but Rust's borrow checker acts as a safety net even for AI scaffolded logic. Finally, TypeScript is your weapon for the interface and full-stack connectivity. It provides the type safety necessary to ensure that the data coming from your AI backend doesn't crash your front end. In the field, we call this the safety speed intelligence triangle. Python gives you the intelligence, libraries, Rust gives you the safety, memory, and TypeScript gives you the speed of development across the stack. If you master this combination, there is almost no modern problem you cannot solve, but writing the code for these is only half the battle. How do you actually direct an AI to build these architectures? The answer lies in how you structure your prompts for entire systems. Stop prompting for a function that sorts a list. In 2026, we move to agentic workflows. This means you prompt for architectural skeletons. You define the interfaces, the data models, and the communication protocols, and you let AI agents generate the connective tissue. For example, instead of writing code, you might describe a CQRS pattern with specific event schemas and ask the AI to scaffold the entire microservice structure in Rust. You become a reviewer of architectural patterns. You must learn to use context injection, providing the AI with your existing system's architectural constraints, security policies, and performance goals before it writes a single line. In practice, this looks like managing a team of AI developers where you are the lead engineer. You define the definition of done and the testing suite, and the AI performs the labor. This requires a much higher level of abstraction than we are used to. If you can't describe your system's design patterns clearly, the AI will give you spec code that works but is unmaintainable. This approach saves time, but it only works if you know which features are worth your time to learn manually. Let's look at the efficiency rule for learning. Finally, apply the 80-20 rule to your learning. In the AI era, 80% of language features are searchable or promptable. You don't need to memorize every standard library method. Spend your 20% of effort mastering the things AI is bad at: complex concurrency, niche performance tuning, and cross-system debugging. When a production system goes down at 3 a.m. because of a race condition, the AI won't always have the logs it needs to solve it. You will. Focus on learning how to read code faster than you write it, because in 2026, you will be reading 10x more code generated by AI than you actually type. Your value is in your ability to spot the one line in 1,000 that will cause a memory overflow in a month. This roadmap, moving from syntax to systems, from code to domain, and from functions to architecture, is how you stay relevant while everyone else is being replaced by a prompt. We've covered the what and the how of learning. Now, it's time to put it all together. In the final chapter, I'll show you how to combine these skills into your unfair advantage, the final edge that makes you a 10x engineer in the age of AI. When you're at the crossroads of your career in 2026, the language you choose isn't just about syntax anymore, it's about which AI ecosystem you want to inhabit. In the field, we see Python maintaining its dominance because of its role as the glue for AI models, while Rust is surging for performance-critical infrastructure. If you are building high-load systems, the memory safety of Rust prevents the kind of production disasters that the LLM-generated C code might introduce. On the other hand, Python's pedantic and FastAPI ecosystems allow for rapid validation of AI-generated logic. Use this decision matrix to align your technical choice with the market demand for either rapid iteration or extreme reliability. Choosing based on trendiness is a trap. Choosing based on the failure state you want to prevent is the senior way. But even with the best matrix, you'll fail if you don't take the first step correctly, which is what we'll tackle next. Knowledge without application is just noise, especially in an era where an LLM can hallucinate a perfect-sounding but non-functional explanation. Your immediate action item is to stop tutorial hell and start agentic prototyping. Pick a boring, repetitive task at work, perhaps a log parser or an automated report generator, and use AI to build the first 80%. Your real work begins in the remaining 20%, auditing the security vulnerabilities, optimizing the database queries, and ensuring the code follows clean architecture principles. This verify-first approach is what separates a senior engineer from a prompt operator. Start by setting up a robust CI/CD pipeline for even your smallest projects, as this structure forces you to think about the software lifecycle rather than just the code snippets. Taking action is great, but there's a philosophical shift you need to survive the 2026 job market. We are entering an era where the human in the loop is the ultimate bottleneck and the ultimate safeguard. In the past, we were valued for our ability to memorize APIs and type quickly, but in 2026, those skills have been commoditized. The unfair advantage you hold is the ability to understand context, something AI still struggles with in complex, legacy-heavy environments. Your value lies in being the conductor of an AI orchestra, where you define the interfaces and the AI fills in the implementation details. As we've seen in real-world outages, AI can generate code that looks correct but fails under specific edge cases or race conditions. Your role is to anticipate these failures before they hit production, moving from a coder to a systemic architect. The developer who survives is not the one who writes the most code, but the one who ensures the right code is written. You might still have lingering doubts about your place in this AI-driven world, so let's address the elephant in the room. To close this journey, let's address the anxieties I hear most often from junior and mid-level developers in the field. People ask if learning low-level fundamentals like memory management or data structure still matters when AI can optimize code for you. The answer is a resounding yes, not because you'll write them from scratch every day, but because you cannot debug what you do not understand. If an AI suggests a B tree for a specific search problem, you need to know why that's better than a hash map in that specific context. AI is an accelerator, but if you don't have a steering wheel, you're just heading toward a crash faster. Stay curious, stay skeptical of magic solutions, and keep your focus on solving business problems rather than just chasing the latest framework. This mindset is your true unfair advantage in the 2026 landscape. While this concludes our current roadmap, the evolution of AI-driven engineering never stops, so keep your tools sharp for the next wave of innovation.